All right, welcome to module number 15. We just finished in the previous module. We were discussing different typical modern types of computing systems. And we went from simple computing systems with a single core to multi-core massively parallel systems. And to understand this, it's helpful to have computational models for parallel processing, which is what we're going to discuss now. So earlier we had the random access machine model, and the random access machine model supported one instruction at a time. And now we have a parallel random access machine, or PRAM model. And whereas earlier, the random access machine model was serial, it supported one instruction at a time, no parallelization at all. Now we do want to support parallelization. So you can look at this sketch here of a possible prototypical PRAM. There's a program, and it's running on different computational units, P1, P2, up to Pn, different processors, and they might be sharing memory. And we want to model this PRAM machine. And the parallel architecture, as we discussed for GPUs, it can have a lot of details, quite complicated, intricate, and we want to capture the main stuff in our PRAM model. We're going to assume that time equates to parallel memory accesses. A read or a write, doing all of them for all of the units is going to take 1 unit time. Now, even without a precise and expertise in the hardware, in the chip design, we understand that if the number of processors grows, writes and reads will take more time. We understand it's complicated. This requires resources, but that's going to be our assumption. Another type of assumption is going to relate to the flavors of different types of memory access. A concurrent read means that the PRAM algorithm can read simultaneously. Different processors will read from the same location. So you could have 1,000 cores, and it's not necessarily that all the 1,000 will read from the same place, but maybe could be that 10 of them will read from location 1, another 20 will read from location 13, and so on. And you can imagine that implementing this, supporting this in your hardware is complicated. On the other hand, an exclusive read means that you never read from the same memory location with more than one core, more than one processor. And that may be simpler to implement. Now, just like we have concurrent reads and exclusive reads, either reading from multiple processors at a time, same location, or just one processor at a time, another question is, are we going to write in a concurrent way or exclusive way? Now, reading, you could say, hey, there's one actual object in that location in memory. If we need to bring the contents of that memory to 17 places, at least it's consistent. But what if 17 processors are trying to write to the same place 17 different things? So the whole idea of what does a concurrent write mean, that might be complicated. So we can understand that there are different types of PRAM machines, exclusive reads and exclusive writes, EREW, concurrent reads and concurrent writes, CRCW, and 2 styles in the middle. And it's probably becoming clear that the concurrent types of machines are very complicated. The exclusive read, exclusive write types of machines are maybe not quite so complicated. So if you have a model or an implementation for CRCW, so concurrent read, concurrent write, you can do complete parallelization at the same time. That type of machine can support an exclusive read, exclusive write algorithm. So there are machines, there are actual machines that run, and then there are algorithms, and an EREW can run on a CRCW machine. However, if you have an EREW machine, it cannot do 17 writes to one location. And because of that, CRCW code, CRCW software will not be able to run on that machine. So there are issues here of the actual machine and the actual hardware and the actual algorithm. So we can see that an EREW machine is, well, calling it simple hardware may be an exaggeration, but at least it's easy to envision. And therefore, it's faster, it's less expensive, and so on. A CRCW machine would require complicated hardware, it's costly, it's slow. Synchronization between different cores can be complicated, and basically CRCW algorithms, at times they have lower computational complexity than exclusive read, exclusive write, meaning that as the problem size scales, let's say maybe you can perform a sort of n numbers with n computational units, or even n square or some other polynomial in n computational units, and you might be able to do that very, very quickly, or at least faster than n log n, but the constants may be worse. So each command, you're growing like n log n, but or instead of growing like n log n, you may be growing like, let's say, square root of n, but typically the constant in front of the square root of n is going to be larger than the constant in front of the n log n. So that'll be it. This was a rather abstract topic. You're not going to be encountering this much. And the next several modules are going to be starting to take a look at data structures.